Okay, so we're going to look at an implicit differentiation question. So in this case, our relation is y squared minus 4xy minus 16 is equal to x squared, and we want to find the gradient of that relation at a particular point. So we need to use implicit differentiation in this case. Well, it's not that we absolutely need to. What else could we do? We could rearrange this to get y by itself. We'd have to complete the square. And then if we had y as a subject, we could differentiate it as normal using the product rule, quotient rule, or whatever was necessary. But we don't need to do that. We can differentiate both sides as a function of x, and that's called implicit differentiation. Okay, so we want to differentiate both sides with respect to x. Thing is though, we've got y in here and y itself is a function of x. So in order to do that, we're going to need to use the chain rule. And as a quick review, the chain rule is useful for when we have a function inside a function. So for example, bracket sine x bracket squared. How would we differentiate that? We would let u equal sine x, and we could find du dx, y would be u squared, and we could find dy du, and then we could multiply those two things together. Okay, so actually that's the same as what we're going to do here, because we've got y squared, and here we had u squared, but essentially it's the same thing, the variable is just different. So to differentiate y squared, we would then multiply it down the 2 to get 2y, but then we need to multiply by the derivative, which is dy dx. Okay, so we've done that using the chain rule. For the next term, the 4xy, we're actually going to need to use the product rule because we have x times y and y itself is a function of x. I'll just pull the 4 out and then we differentiate the first one. So derivative of x is 1 times y plus x times the derivative of y, which is dy dx. Okay, so we've done that there using the product rule. Next thing we need to differentiate is 16. Well, that's easy because derivative of a constant is just going to be 0. And on the other side is straightforward as well because the derivative of x squared is just 2x. So essentially this is what we have for our derivative. We can see dy dx appears twice in there, but that's not a problem. We can just expand this and rearrange to get dy dx by itself. So I would have 4y minus 4x dy dx is equal to 2x. Now I could sub my x and y values in here, or I could isolate dy dx, which is what I will do in this case. So I'll move the 4y to the other side. And I've got two terms with dy dx in them, so I can take out dy dx as a common factor, and I would have here 2y minus 4x. Okay, and then dy dx would be equal to 2x plus 4y over 2y minus 4x. Now, we need to put in our x and y values to find the gradient at this specific point, and the point we want is x is equal to 2. Well, we don't have the y value, but we can find it using our original expression or relation. So we know that when x is equal to 2, this relation is y squared minus 8y minus 16 is equal to 4, and we can use that to solve for y. It's a quadratic, so we could factorize it and solve, and we would get two solutions, which are y is equal to -2 or y is equal to 10. We're told that we have to be in the first quadrant, so we know then that we cannot have y is equal to -2, we must have y is equal to 10. Okay, so we put in x is equal to 2, y is equal to 10 into our expression for dy dx. And if we do that, either by hand or in the calculator, we should find that dy dx is equal to 11/3. Now, I should just mention that if we did have a calculator here, if this was our exam 2 for VCE Specialist Maths, we could skip a lot of these steps and just use the function for implicit differentiation on the CAS calculator. So if it's a TI Inspire, it's under Menu, Calculus, Implicit Differentiation, and the syntax is how it's written here. So we have our relation, comma x, comma y. And then we can sub in, given that x equals 2 and y is equal to 10, we would still need to do a step in order to solve for the y value when x is equal to 2. Okay, but this could easily be an exam 1 question, and if it were an exam 1 question, then the process that I've outlined here hopefully is clear for how we do implicit differentiation.